Hey everyone, welcome to day one of online learning. Today we're starting a new unit. We're going to define an exponential function and then differentiate between an exponential growth and exponential decay. And then I'm going to teach you how to graph exponential functions just by creating XY charts, which is how you were originally taught to graph things way back in middle school. So let's start. What is an exponential function? Here's the definition. An exponential function has x as an exponent. So you can see these are all examples of functions, and the x variable is an exponent in all of them. That's what all three of them have in common. That's what makes all three of these functions exponential. All right, so if you ever see your variable is an exponent, that is the definition of an exponential function. These functions all look different, but that's the one thing that unifies all of them. That's the one thing that defines them all as exponential functions. We are going to differentiate between exponential growth, which I'm talking about right here, and then in a moment we'll talk about exponential decay. So here's exponential growth. This might be kind of confusing to see. If your function is in this form and the base is greater than 1, it's considered an exponential growth function. So here are two examples of exponential growth functions. Let's talk about why both of these meet this definition. So we have the x as an exponent. That's what makes it exponential. But here's the base. And since this base is greater than 1, that makes this specifically exponential growth. This one's a little bit more confusing. We have the x as an exponent. And remember, that exponent only applies to the 4. It does not apply to the 1/2. So when we say up here that b has to be greater than 1, we only care about the base being greater than 1. So the base in this example is 4. That's obviously greater than 1. It doesn't matter that this 1/2 isn't greater than 1. In order to be classified as an exponential growth function, it's just the base that has to be greater than 1. So that's why both of these are examples of exponential growth. Here is your classic graph of an exponential growth function, and we are going to have to talk about how to graph these. But let's just talk about the classic characteristics of an exponential growth function. The right side of the graph has an upward facing arrow. So that's what you see here, right? This is the right side of our graph. That arrow is pointing up towards infinity, upward facing arrow. If I wanted to translate this sentence into a more mathy phrase, it would be this. We're talking about end behavior, which we talked about all year. As x approaches infinity, f of x approaches infinity. So all this means is as we move to the right on our function, our y values are going up to infinity. So this is just like a math translation of exactly what this sentence above it says. These two things mean the exact same thing. The left-hand side of the graph approaches a horizontal asymptote. What the heck is an asymptote? It's a new word. That's a line that your function gets closer and closer and closer to without ever touching it. So it might look like this blue function is actually touching the x-axis. It's not. It's getting infinitely close to the x-axis, and it's getting closer and closer and closer the further we move to the left, but it will never touch that x-axis. That's a word we're going to use a lot in the upcoming days, so remember that. Asymptote is a line that a function gets infinitely close to without ever touching. And then this graph is just kind of your classic picture of exponential growth, but exponential growth functions don't always look like that. This is another example of an exponential growth function. You can see it's been shifted up a little bit. So the asymptote is here as opposed to at the x-axis. Here's another example of an exponential growth function. You can see that it's been shifted downwards so that the asymptote is down here instead of at the x-axis, but they're all exponential growth. They all have these classic characteristics of an exponential growth graph. All right, let's talk about exponential decay. So if this is what your function looks like, it is exponential decay. So in this scenario, it's exponential decay if your base is between 0 and 1. So these are all examples of exponential decay functions. There's our x, it's an exponent. And here's the base, it's 1/3. Since 1/3 is between 0 and 1, this f function is classified as exponential decay. Same deal down here with h, right? X is your exponent. 0.5 is the base. And since 0.5 is between 0 and 1, this classifies as exponential decay. This last one is the most confusing, that 6 is there to throw you off. Once again, that x exponent only applies to the 1/7. It does not apply to the 6. So 1/7 is the base. And since that base is between 0 and 1, this is classified as exponential decay. The 6 doesn't mean that it's classified as growth because it's this base that has to be between 0 and 1. And here are the characteristics of an exponential. Oops, that says exponential growth. It's not supposed to. Let me change that. All right, so in exponential decay, we see kind of the opposite that we saw with exponential growth. It's the left-hand side of the graph that has an upward facing arrow. So this is what's pointing up, whereas in exponential growth, it was the right arrow that was pointing up. If I wanted to phrase that in math terms, I could say as x approaches negative infinity, so that means as we move to the left on our graph, the y values are approaching infinity. All it means is it shoots up towards infinity. And then in this case, the right-hand side of the graph is what's approaching the horizontal asymptote. So that's exponential decay. And not every exponential decay function is going to look exactly like this. Sometimes they're shifted up, sometimes they're shifted down, sometimes they're shifted to the right or left. But this will always be true. The left-hand side will always be pointing up towards infinity, and then the right-hand side will always be approaching a horizontal asymptote. Now let's actually talk about how to graph these things. If I give you an equation and just tell you to graph it, we're going to kind of revert back to our Algebra 1 roots, creating an XY chart. So I already have the X values filled in here. And if in the future I ever don't give them to you, just plug in -3, -2, -1, 0, 1, 2, and 3. All right, and that'll give you a pretty good picture of what the exponential function looks like. And in the future, y'all can just use your calculators and generate decimals. I'm about to do this using fractions, but in the future, you guys can do it with decimals. That is totally fine. So it's honestly just kind of a plug and chug for you. We'll only go through it with fractions once right now today. So if I want to find what you get for y when you input in -2, that's what I do. I replace the x with -2, and then I just have to evaluate this. I could plug it into my calculator, but that's going to give me a decimal, and for just tonight, I want to do it in terms of fractions. So hopefully you all remember from last unit what happens when we have a negative exponent. The entire term flips, right? So this 2 to the power of 2 flips into the denominator and the exponent becomes positive. And then all we have to do is evaluate what is 2 to the power of 2 is 4. So our y value is 1/4 when our x value is -2. I'm going to go through the same process for all of these x values, right? If I plug in -1, same deal. This entire term has to be flipped into the denominator, and then I just have to evaluate 2 to the power of 1, which is 1/2. Plugging in 0, this might be something you forget from last unit. Any number to the power of 0 is 1. That's just something you need to remember. Plugging in 1, 2, and 3 are easier. 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8. And then all you have to do is plot these points. Am I going to be able to plot 1/4 and 1/2 perfectly? No, that's okay. Plot the points that look something like that, right? You can see all my points right there. Is that perfectly 1/4? No, but we'll go with it. And then you have to connect all of those points using a smooth curve. And it helps that we just looked at examples of exponential growth and exponential decay functions. You kind of know what they're supposed to look like. They look like this. All right, so we have a horizontal asymptote here, and in this direction, our values are shooting towards positive infinity. And if you actually look at these numbers, it should make sense why we have a horizontal asymptote in this direction. Let's say I was to continue to plug in x values. If I was to plug in -3, and then -4, and then -5, my denominators would keep getting bigger and bigger and bigger, which would mean that the entire fraction was getting closer and closer and closer to 0. So that's why we have an asymptote in this direction, right? It's getting closer to 0 because our denominators are getting bigger, but it's never going to get there. Domain and range, everyone's favorite friend. So you guys should be able to get the domain of this thing and the range of this thing on your own, even though we've never talked about exponential functions specifically. We have talked a lot about domain and range. So take a second just to think about what they are. Remember, domain is all about x values. We can see that this thing is pointing to the left forever and to the right forever. So it spans all possible x values. Its domain is negative infinity to positive infinity. And its range, this one's a little bit tricky, right? The lowest value, you might be tempted to say, is 0. But we just talked about how this is an asymptote. The function does not actually reach 0, which is why I'm using parentheses instead of a bracket, right? This means that 0 is not actually included in the range. So our lowest value is 0, not including 0, but then it goes up infinitely high towards infinity. So that's our range. All right, let's continue. So this is how we're going to graph every time. We're going to create an XY chart. If I give you the X values, just plug them in. If I don't give you the X values, use -3 to +3. All right, so look, X value of -2. I replace the X with a -2, and then all I have to do is evaluate. In the future, y'all will do this with a calculator and just get a decimal. For now, I want to show you what the fractions look like. So 1/3 to the power of -2. Remember that negative exponent applies to the 1 and the 3. So they're both going to flip locations, right? That's what negative exponents do. They make things flip. That just becomes 3 over 1. That 2 exponents applies to the 3 and the 2. You can see how stuff from last unit is still important, which simplifies to 9 over 1, or just 9. 1 works similarly, right? I plugged in -1. The fraction flips, right? It becomes the reciprocal, and the exponent becomes positive. And then that just simplifies to 3. You raise any number to the power of 0, you get 1. That's a rule from last unit. We got to remember that. 1/3 to the power of 1 is 1/3. 1/3 to the power of 2. Remember that exponent applies to both numbers in the numerator and the denominator. So if I wanted to simplify that, I could write it like this. That becomes 1/9. Raise it to the power of 3. Could rewrite it like this. If I evaluate the numerator and the denominator, I get that. All right. If I were to keep plugging in points, right, 4, 5, 6, 7, 8, the denominator would keep getting bigger and bigger and bigger, which would make the entire fraction closer to 0. So can I accurately plot 1 over 27? No, but it's really close to 0. So I've just done my best when I plotted all those points to make it as close to 0 as possible. We know what exponential decay looks like, right? This is a decay function because that's less than 1 and greater than 0. So I draw in that curve. Once again, the domain, it goes all the way to the left forever and all the way to the right forever. So the domain is all real numbers. And the range is 0 with parentheses, without a bracket, because it's never actually going to hit 0, up forever towards infinity. All right, so this is the last one we're going to graph today. This is how we're always going to graph these. We're just going to create an XY chart. If I give you the X values, use those. If I don't give you the X values, plug in -3 through 3. So I want you guys to actually pause the video right now. Using your calculator, plug in all of these X values and see if you can get Y values. It is okay to just write them as a decimal. That is totally fine. So pause the video because I'm about to put the answers up. You should get all those. All right. So then you just have to plot those points. I already plotted it. Are we going to be able to plot -6.88 perfectly? No, that's totally okay. You can see that it's approaching -7. If I were to keep plugging in values, -3, -4, -5, -6, it would get closer and closer and closer to -7. So that is our horizontal asymptote. Let's talk about the domain and range. The domain, once again, is -infinity to infinity because it goes to the right and left forever. And the range is -7 to positive infinity, right? Because it doesn't, lowest point is right here, but it never actually gets to -7. So that's why it's a parenthesis, not a bracket. And then it goes up forever towards infinity. Last thing I want to talk about, this is the horizontal asymptote. I could ask you to write the equation of that horizontal asymptote. That's just the equation of a horizontal line, and it would be x equals -7.